I would like to start recording. So this is the schedule for the day. First of all, me and Manuel will briefly introduce CIGRE UK NGN and Austria NGN. And then our first speaker, Lukas, will present on lightning phenomena in the Alpine region of Austria. And then Dip, our second speaker, will present on the effect of network parameters on the transient overvoltage phenomena during system restoration. Brief introduction of myself. My name is Ying Xue. I'm the Secretary and Treasurer of CIGRE UK NGN. I'm also a lecturer in electrical power networks in the University of Birmingham. My research largely focuses on HVDC, high voltage DC transmission and power system simulation technologies. Now I would like to briefly introduce CIGRE UK NGN to you. The purpose of the NGN, which stands for the Next Generation Network, is to act as a gateway to the CIGRE and also a platform and a professional network for the engineers and young researchers to exchange ideas and interact. We have a strong leadership team, or the steering committee of the NGN, with steering committee members from different companies, as you can see from the right in the UK. And also we have steering committee members from different leading universities in the UK as well. We were set up in 2007, so more than 10 years, and we are the first CIGRE's young member group. We currently have around 240 members, around 40 of them from students or researchers, and around nearly 60% of them from industry. We welcome everybody to join the NGN because first of all, it's free for the students and first 3 years for the young professionals. And you will be able to join, you have the opportunity to go to various CIGRE NGN events, and then also to join international working groups, and to support the shadow study committee panels, to join the NGN steering committee, and also publish papers in working groups and CIGRE conferences. And last but not least, you do not have to be an expert to join, as long as what you are doing or is related to the power system research or power industry. Another benefit is that if once you join the CIGRE NGN, for example, through the Young Member Showcase, which is initiated by the UK NGN, you will be able to present your work in the Paris session, which is a biannual technical congress and exhibition in Paris. For example, in 2018, it attracted over 3,000 delegates and more than 6,000 exhibition visitors. We had, for the CIGRE UK NGN, we had a number of previous events. As you can see, for example, we have site visits to the HVDC Western Link, and also the VSC demonstrator in the previous Alstom grid, and also the Norwich Power Station and other power stations in the UK. We also have technical competitions, for example, the Young Member Showcase, and a number of other technical workshops. For the more recent events, at the end of the last year, we went on a Nelson substation visit in collaboration with University of Strathclyde in Scotland. And at the same time, we will also be able to see or listen to the technical presentation on one of the flagship multi-million-pound project funded by Ofgem called Phoenix Project. End of last year, we also had the opportunity to take on an educational event at East Cambridgeshire Careers and Skills event, where we welcomed over 1,000 primary and secondary students to promote interest in power industry. Early this year, we had our Young Member Showcase for 2020, where we have 10 candidates shortlisted and 4 winners nominated. During that event, we also went on a lab tour at the University of Manchester, including the high voltage testing lab here on the right. After the start of the pandemic earlier this year, we were not able to have face-to-face workshops or meetings. Then we switched online. In June, we had one on wind energy in collaboration with the CIGRE Island NGN. In August, we had 3 in collaboration with IEEE's University of Manchester branch. Another one with CIGRE US National Committee. Another one in 19th of August in collaboration with University of Birmingham. And the last one we had is in 2nd October which is on offshore wind energy in collaboration with CIGRE Denmark NGN, with two speakers from the UK and 2 speakers from Denmark. So last but not least, we have launched the mentoring scheme at the CIGRE UK NGN. So if you are willing to join the mentoring scheme, where you will have the rare opportunity to learn from experienced and technical experts in the CIGRE UK. So please, if you are interested in this, please let us know through this email. And if you are interested in future events, you can follow us on the LinkedIn page, Twitter, and also subscribe to our newsletter. So thank you very much. That's a brief introduction to the CIGRE UK NGN. So if you're interested in it, please let us know. If you have any questions now, you can type into the chat box, or you can send me an email later, and I will be able to answer your questions once Manuel finishes his part of the presentation. So thank you very much. I will now carry on to introduce Manuel Gala, who is currently the chair of the CIGRE NGN Austria. Since 2018, he's employed as the university assistant at the Institute of Electrical Power Systems at Graz University of Technology. His main research focus is the investigation of the grid interconnection behavior of power electronic equipment using hardware-in-the-loop technology. Now I would like to stop sharing my screen. And Manuel, could you please start sharing your screen and your part of the presentation? Thank
you. Yeah. So, screen should be shared, right?
Yes, it's in presentation mode. You may switch to.
Okay. Now we have it, right?
Excellent.
Okay. Yeah. Ying, thanks for the introduction and also for the general information about NGN UK and also in general about the NGA organization and how it works. Now I will give a brief introduction to the NGN Austria. I will start with we established at 2019, so we're quite young. We're in our 2nd year. We had an event on the 24th of January, supported by Professor Uwe Schichler. He's the patron of the NGN Austria, and he's also a member at the National Committee in Austria. Here we have the members which were directly able to visit the established of the NGN network. And the first ever elected chair was me in 2019. You can see me here with Professor Schichler. At the beginning, we had 15 NGN members in the first year. So this we started directly with 50 because we had already some student members, and we shifted all the student members directly to the NGN organization. So that's the reason why we directly started with 50 members. Our annual general meeting was this year also, and the introduction to the election of Austria NGN committee, which were elected at the 3rd of March, was again me as the chair. We had an election of a vice chair and an election of a secretary, so it was no longer a one-man show. It's now really an board of the NGN. You can see all 3 people here in the picture. On the left side, you see Mr. Bischler, the vice chair, and on the right side from me is Mr. Riegler, and I'm in the middle of the picture. The community increased to 70 members, so we were able to gain 20 more people to the NGN, not only from the student side, from the university, we also were able to get some young professionals, and we also tried to gain these members. What happened? At 2019, we were able to visit the first time the National Committee meeting. So also in the future, we are able to bring in our topics directly to the National Committee, and we're attending the National Committee meetings. We're attending the third Vienna conference. So this is the Southeastern European Regional Council, which has a big conference normally it was planned in 2020, but you all know due to the situation, it was postponed to 2021. And we are able to assist for some NGN events. So we are planning some directly NGN events at the conference and also beside the conference. So some meetings and some joint ventures. We are in a cooperation with the CIGRE organization, and responsible is Ms. Kerstin Weindl. At that point, I also want to say thank you to Kerstin, because she was responsible for the organization today from our side and was organizing the timeline and something like that. The Austrian NGN community meeting was this year online. So we try to get in contact with our members, but yeah, most likely it's actually not that easy. So we made an online NGN community meeting, and we had also a technical lecture there from a professional. He was talking about geomagnetic induced currents and the behavior to transformers and grids. So it was quite interesting, and we're planning to do more of that events. Also, I'm proud to say that we were attending the NGN showcase in Paris, so the e-session this year. We were able to send 2 Austrian NGN members, so 2 of them were accepted for the e-session. It was Martin Hayden and also Michael Spiegel with the topics. So what we want to do at the next time, so our outlook is the next CIGRE Austrian National Committee meeting will be held next month. So I will attend this meeting and can again bring up the actual topics of the NGN Austria. We are in the planning phase of the second NGN Austria community meeting, online for sure, to have again the possibility to bring up the NGN information from Austria and also from worldwide directly to our members. And we are focusing on the second part of the NGN Austria community meeting, which will be a technical lecture again. It will be held online, and the annual general meeting from NGN Austria will be held at the beginning of 2021. And we are focusing on expanding the regional NGN network. So we gained 20 people, 21 members, and we focusing more to gain more members from research institutions and universities. Actually, we're quite focused on universities. Now we try to keep the focus on the research institutions, that we gain more young professionals to our NGN. We're planning also a joint venture with the National Electrical Engineering Association. It was planned for today, but not for today, so for this year. But yeah, we shifted it to next year, and hopefully we can meet up in person, because this association has also a department for young engineers, and we want to meet up face to face, that we can know each other a little bit better and drink something together. Here are the information of chair, vice chair, and secretary. And yeah, if you need some information or get in touch with us, just write us. And I'm looking forward now to a very nice joint webinar from UK and Austria. Thank you.
Thank you very much, Manuel, for the nice and brief and concise introduction on the NGN, CIGRE NGN in Austria. So now let me share my screen again. Now I would like to introduce our first speaker for the day, who is Dr. Lukas Schwalt. Dr. Lukas Schwalt is a postdoc researcher at Graz University of Technology, Institute of High Voltage Engineering and Systems Performance. He successfully defended his PhD thesis at Graz University of Technology in 2019. His main areas of research include cloud to ground lightning, measurements of lightning discharges, performance of lightning detection systems, lightning protection concepts, and transient voltages on power lines. He's involved in the Austria Association for Electrical Engineering, CIGRE B2 and C4, and served as a technical secretary for CIGRE ICLPS in 2019. The title of his presentation is Lightning Phenomena in the Alpine region of Austria. So thank you very much, Lukas. Now, could you please start sharing your screen?
Of course, thank you very much for the kind introduction. You should all now see my screen.
Yes.
So I'm happy to be here. As you heard, my name is Lukas Schwalt. I'm with Graz University of Technology in Austria. And now today I would like to take this opportunity to talk to you about my research and my PhD topic, lightning phenomena in the Alpine region of Austria. So my object today are the lightning phenomena, but for that reason I would like to give you an overview of general lightning characteristics at first, that we are all on the same page. First of all, you have to know that there are cloud-to-ground lightning flashes, but also cloud strokes. On the right side, you can see such a cloud-to-ground stroke. There is a channel starting from cloud, reaching ground, and this is then having an impact on the infrastructures on the ground, of course. For both of these types of strokes, like cloud to cloud appearing just in the cloud or between cloud, we got a field emission and even a charge transfer. But what we want to focus on cloud to ground strokes now and today. So cloud to ground flashes consist of one or even various strokes. If it's just one stroke, then it's called a single stroke flash, what will be important afterwards. They can appear as downward, so starting from cloud, reaching ground, or even upward from ground to cloud, where upwards are not that frequent. Downward are much more frequent. Of course, there are some current parameters we can discuss. It's, for example, peak current and even current front steepness. You may know these parameters out of standards, and even if you did some simulations via simulation software. So current front steepness is always a factor you have to choose to do some impulse tests, for example. Another parameter is the return stroke velocity in meters per second. So this is still this value is still investigated even after 60 years of, or more than 60 years of lightning research. We don't know much about this value. Let's head on. In order to illustrate the process of lightning discharges, I would like to explain that graphically. First of all, to get a lightning strike, we need a charged cloud or a thunderstorm with a certain charge distribution. Then somehow a preliminary breakdown appears. So here you can see the timeline. After 1 millisecond here, preliminary breakdown appears. Then a stepped leader starts its stepping process towards ground. There we are already at 90 milliseconds. The leader channel is already much longer. And then an attachment process starts even from ground towards this leader head. And in some point they connect then, and that's what we call a first return stroke. And that's what we are interested in today. So this first return stroke can then like glow for a certain time. There are K, Kleine, and junction processes going on in the cloud. There's then a so-called dart leader, where again, charge is positioned along the channel. And then we get the second return stroke. So first and second return stroke, this is the impact then on the ground. And this is that's what we are interested in. So let's switch off the laser pointer, because what I want to show you now, with all the previous knowledge we just learned, we can now watch the process in a high-speed video. I captured this video during my measurement campaign in 2017 at Graz airport, so south of Graz. I recorded this video with a recording speed of 2000 frames per second, and now we are watching this video first with 24 frames per second in slow motion, and then as a frame-by-frame analysis with 2 frames per second. Let's start the video. So 22nd of May 2017. Here you see the first stroke appearing, and then the second stroke to a different ground strike point. Cloud to ground flash. So all in all, we call it a flash with 2 strokes. And you see now a much longer glow where charge is transferred from cloud to ground. Now in 2 frames per second, it's easier to watch it like how it appears. It starts preliminary breakdown, then the stepping process till it reaches ground. There is the first return stroke, a little glow, and it's already off. Then there is something happening in the cloud where you can see that then the start where charge is transferred in the channel. That is the glow in the cloud. Here are also some cloud to cloud discharges, and the second return stroke striking a different ground strike point with a much longer glow now, so a so-called continuing current transferring charge to ground. If you want to or to give you now an impression how the emitted electric field appears here, is again a high-speed video, which one was linked to the electric field in the down part visible by using the GPS timestamp. So we still watch a process with 2 strokes, cloud to ground flash with 2 strokes, but now we are in the region of Zell am See, so in the central Alpine region of Austria. The black and white high-speed video was color-coded, where blue is black and dark is red-white. And here you can now see the initial breakdown, which we saw before on the graphic of slide 4, and even the return stroke of the electric field. Starts, this is the initial breakdown. So now the process starts in the cloud. This is what we can measure as an electric field. Now the channel appears and strikes the mountain top. This is the electric field process linked to this process. Then there is something going on in the cloud, different channels visible. And again, there is appearing a second return stroke in a distance of about 39 kilometers. So this was the main, these were the main characteristics. Let's go on. I will switch to laser pointer. That's all about basics you have to know of lightning processes right now. And now I would like to talk about the motivation for my research project and my doctoral thesis, of course. First of all, you have to know that Austria has high lightning activity compared to other parts in Europe, at least in the southeastern area. You can see that here on the right, you can see a graphic generated by ALDIS, one of our main partners, the Austrian Lightning Detection and Information System, which is operating a sensor network of 8 sensors and processing data of over 166 sensors, lightning location system sensor all over Europe. So to get more information about real occurring lightning strikes in the country, lightning ground truth data, the aim was to gather lightning ground truth data to study the cloud to ground discharges at different locations in the Austrian Alpine region. This gathered data set should then be analyzed regarding its lightning flash parameters, and it shall also be correlated with lightning location system data of the ALDIS network. So Graz is here, that's where I'm situated right now. You may know Vienna, that's over here. And this is the main area of the flash activity. So this picture shows actually the flash density in flashes per square kilometer and year. So the method of investigation was to carry out on-site measurements of cloud-to-ground flashes by using a mobile video and field recording systems at different locations all over or over the most part of the country. So the gathered data shall then be correlated with lightning location system data, and the generated overall data set shall then be analyzed to result analyzed, and the results shall be compared to values from international literature. But before I started my research, we actually had to define a specific field of research, and there we agreed on 4 fields of investigation. That's first of all the correlation of the data with light education system data, the determination of the occurrence characteristics, the analysis, of course, first the analysis, then the occurrence characteristics, and the impact of direct lightning strikes were also analyzed. So today I will focus on the first 3 parts of our field of research. And for that reason, if you want to find some information about direct impacts, I will happily provide you I'm happy to provide you my thesis. As a measurement system, a so-called video and field recording system, or short VFRS, was used for my investigation. The system is composed of a high-speed video camera, which was configured to record videos with a frame rate of 2000 frames per second, which is enough to really see the processes as you already have seen in the videos. The second part of this VFRS system is the electric field measurement system, which was used to record the transient electric field of the appearing lightning strikes. And afterwards, this information was used to get out the polarity of the stroke. All parts are triggered manually if they appeared in the field of view of the camera. Here, like rather small, you can see the trigger box with the green button where I had to press on to get the record running. As already mentioned, each part was GPS time synchronized to get the both of my systems, the high-speed video and electric field, connected or correlated, and then even to correlate it with the light navigation system data. This is then the on-site setup where you can more or less see each component of the measurement equipment. To be flexible in choosing measurement locations in the most part of the country and to avoid any interference of the grid, we used a transportable power generator. So in the picture on the right, there are also the 2 GPS antennas visible. The measurement control devices in the measurement vehicle where you can see a screen and the PXI system. There is the camera, of course, and then there is the integrator, amplifier, and transmitter box, which is used to process the signals of the flat plate antenna and then send it to the measurement and control devices. The 2 main components, the camera and the flat plate antenna, are shown even on the left side. As a camera, a Phantom V9.1 was used, and the flat plate antenna is a development by Aldis. To get an idea of the real measurement arrangement, I also want to show the picture on the left. So the flat plate antenna for all the measurements was placed in a certain distance, about 20 meters, from all the other measurement equipment, again, to avoid electrical interferences. So the picture on the right, if you want so, shows a shrinked arrangement. By using this kind of measurement setup at 21 different locations all over the 3 years, we were able to collect data of 51 thunderstorms. Here at the right side, you can see, first of all, the sensor locations, also my measurement locations, and the cloud-to-ground flashes recorded for 2015, 17, and 18 as a scatter plot. So strokes, you have to know, can have a negative, positive, or bipolar polarity, and we recorded the data for negative cloud-to-ground flashes, including 463 flashes and over 1,500 strokes. So we also recorded 59 positive cloud-to-ground flashes with a positive polarity and 9 flashes with a bipolar polarity. This distribution of all these negative, positive, and bipolar flashes corresponds to the real probability of occurrence according to polarity, which can be found in the literature. In the following, I would like to deal only with the results on negative lightning discharges. So the methodological approach after recording the data was thus divided into correlation of the video and field recordings of VFRS and LLS lightning location system data. Then investigations of specific flash parameters followed, and also LLS quality parameters were analyzed. Today, the single stroke flash percentage per year and for different thunderstorm types will be the most important, and also the mean multiplicity will be of interest. The LLS determined return stroke peak currents are parameters which were investigated too and can be found in my thesis again. For the LLS quality parameter, the location accuracies shall be discussed here. So the location accuracy is one of the two most important quality parameters or main parameters to classify the actual performance of such a lightning location system, sensor system. This is just possible with information of ground truth data, and the value, this value, what you can calculate shows the error of a detection of strokes striking the same ground strike point. The second important value would be the detection efficiency of strokes and of flashes, of course, which can even, again, be found in my thesis. So the correlation started by linking each measurement data set of video, electric field, and LLS data. Then a frame-by-frame analysis of each stroke started. I then even linked it to the electrical field at the moment of the return stroke, checked for the LLS data, and got out some other information as latitude and longitude. What was, for example, checked is here the right classification of cloud to ground stroke. So intercloud 0 means it is classified by the LLS as a cloud to ground stroke, which is correct in that case. And all this information were then entered in a database to get this, as I called it, overall data set. So for the analysis of the location accuracy, I would like to give you a graphical overview to get a better impression of the process. So here we have a satellite map of the lightning location system detections of a flash, including 7 strokes to 2 ground strike points. First ground strike point is visible here. So the first stroke hit this ground strike point or strike this ground strike point, and all the following strokes hit then or strike then this area, this ground strike point. You can imagine this case is similar to the first of the 2 videos. So for the stroke 2 to 7, we should see an overlay of all the detected positions of the LLS calculated strike points. Why is that? Each stroke, as you can see in this frame-by-frame analysis for 2nd, 4th, and 7th stroke, each stroke is following the same channel to ground and striking the same ground strike point. But in the LLS calculations of the strike point, we can see some deviation. How can we now do an analysis of the deviation? For this, we used high-speed video data where we can see that each frame of the 6 strokes looks alike and ends up in the same ground strike point, and then we can define that we can calculate an error between these strike points, because we know that they should all be the same. So satellite map, video recording, and so we can link it then by using the latitude and longitude for each strike point of the ALICE dataset. So that's all I wanted to say about the methodology part of my research. Let's now take a look at the results for one of the investigated parameters, the single stroke flash percentage of negative cloud to ground strokes for the video and field recording system data. The analysis of this parameter resulted in a relatively high amount of 27% of single stroke flashes for the total data set. The annual variability of these parameters was 24 to 29%. And so for all years, it was higher, or at least at the top of the values reported in the literature, which start at 12% and go up to 24%. So we then started to investigate what could be the cause of this deviation by classifying each analyzed thunderstorm in a specific type of thunderstorm by using two discrimination parameters. One was weather data and the second was the vertical wind shear. But even that discrimination resulted in values around 26 to 27% of single stroke flashes for each individual thunderstorm type. So we are still investigating why these numbers are so high in Austria. At the right side, you can see again the picture you saw before, but now for all in all negative flashes and negative single stroke flashes in a different color. And you can see that these are spread over the country. What is an advantage of using such ground truth video data to do such analysis is that we don't have to worry about an influence of wrongly classified cloud-to-cloud flashes by the LLS, because we excluded that by using this ground truth data. Let's move on. Such high values of single stroke flash percentage or single stroke flashes in general, of course, have an influence on the multiplicity values. So the strokes per flash, if you want. So these multiplicity values, or the mean multiplicity values, are typically used in lightning protection standards, and especially for lightning protections of transmission lines. Even in several CIGRE brochures, they used the mean multiplicity values. And we can here compare the VFRS data and the LLS data. So the mean VFRS data multiplicity value is situated at the lower end compared to numbers in the literature. So we got 3.3. That's similar to the lowest value reported in the literature. Excuse me. And it goes up to 6.4 strokes per flash. What was interesting to see here is that we were able to detect a drop of the mean multiplicity value for the lightning location system data in 2017 and 2018 to 2.8 as a mean value. After some investigations, we found out that the new sensor software differentiation between intra-cloud, so cloud-to-ground strokes and cloud-to-cloud strokes and cloud-to-ground strokes had a bug. So this bug was already corrected by an update in 2019 after reporting it. At the right side, you can even see the distribution of the multiplicity of the VFRS and LLS data with a maximum value of 15 strokes per flash recorded with the VFRS. So 15 strokes within 1 second appeared there in a certain area. Results on the location accuracy. So that's the parameter I wanted to discuss regarding the LLS. That showed a good, or let's say low values over the 2 years of investigations. They varied from 90 to 130 meters. The median location accuracy for all the data set was 100 meters. And for such an analysis, it's again highly valuable to get data over a great part of the country to check all the different areas. Here again, a bug in a sensor software update was detected, which caused a larger value of the 95% location accuracy statistical parameter to 2.8 kilometers. And it decreased again in 2018 to 0.9 because they did another update. The picture on the right shows again a distribution of the location accuracy value in kilometers, where you can see that most of the location accuracy values are situated in an area of 100 meters. Let's start now with the conclusion of the analyzed lightning parameters. So ground truth measurements have been used after their recording to evaluate the lightning activity throughout the country. a high percentage of single-stroke flashes have been detected compared to values of international publications. Even an analysis of single-stroke flash percentage for different thunderstorm types showed similar results for all kinds of thunderstorms. That, of course, led to a lower mean multiplicity value, which is situated at the lower end compared to literature values. As a conclusion for the LLS quality parameter, we can conclude that our gathered data provided high quality ground truth information for performance evaluation of the lightning location system. The results for the analyzed location accuracy showed an ongoing improvement for the median location accuracy and even for the 95% location accuracy. And this is caused by sensor updates and improvements of the sensor technology. Again, a picture of a lightning strike, like a so-called forked stroke, double strikes at the same time. Last but not least, I would like to sum up my presentation. I performed an analysis of cloud-to-ground lightning phenomena in the Alpine region of Austria after recording a ground truth dataset. So the measurement resulted in a correlated dataset, overall dataset of 531 cloud-to-ground flashes, including more than 1,600 strokes. My analysis showed a high percentage of negative single-stroke flashes, but a mean multiplicity value, which is comparable to values reported in the literature, was detected. We saw also that the analysis of the lightning location system quality parameters showed constantly high values, at least for the location accuracy, but I can say even for the detection efficiency. Now, before I conclude my presentation, I wanted to show you a last video of such an impressive flash with several ground strike points and a lot of strokes going on, recorded again with 2000 frames per second, and now here shown with 10 frames per second. That's a measurement from Austria, of course, from Southeast Austria, I wanted to say. I just have to uncheck the laser pointer. Now the video should start, and you will now see in a section of 700 milliseconds, a lot of strokes going on, coming from different areas of the cloud, striking different ground strike points. We saw already 3 now left. There is the next one coming. Now we are already again in the middle of the section of the video. Another strike point, some cloud-to-cloud strikes going on, another stroke to another ground strike point, and now again something will appear here. So a subsequent, so-called subsequent stroke in a formal generated channel. That's it. We see here now a long continuing current, some cloud-to-cloud strokes going on again. Yeah, it's again, every time I see this video, it's impressing for me. And now I would like to conclude. Thank you all for listening and for having me today as a speaker. If there are any questions, don't hesitate to ask. Thank you.
Thank you very much, Lukas. Thank you for your very interesting presentation. And I think the lightning phenomena in any country, the research on it should be of interest to not only itself, but also to the power system as well. I can see there is one question from the chat box asking, where can you find that camera?
That's a good question. So the camera is was actually coming from Brazil. So we used one INPE in Brazil bought, and the manufacturer is called Phantom. I'm sure I can say that. This is a manufacturer from the USA, but there are plenty of manufacturers which are now producing these high-speed video cameras, and like 2000 frames per second is not even a fast camera anymore. Now we are up to 1 million frames per second, and even more, even 2 million frames per second are available.
Okay, thank you very much.
You're welcome.
There's another one coming in. Why south part of Austria has higher lightning activity?
Yeah, that's quite a good question. So that appears because of the situation with the Alpine region and the southeastern part where it's rather flat, so nowadays we think, but we are not totally sure. We think that it's something about the geographical arrangement, and there we have to say the research is still going on. So to define where a lot of lightning strikes appear and where not is rather difficult. If you look on a big terrain area, it's easy if you just check for some spots, like if it's maybe a sea side and then a mountain area appears, then thunderstorms are forced to appear, and so even more lightning is appearing. Yes. Here you can see, again, such a thunderstorm in the middle of the Alpine region, there where I recorded some of my videos.
Okay, thank you very much. I have another two. The first one is, have any changes been observed in lightning frequency characteristic in recent years that might be linked to climate change?
Yeah. I just recently received one of the newest books about lightning research and even impact of lightning strikes on power systems. It was handled by Alexandre Piantini from Brazil, and the first chapter there is lightning and climate change. So that's now to 2020 is the first year where I saw really a book coming out with a chapter lightning and climate change. We can nowadays say that if we're looking at some traveling routes of ships, that there appear lightning strikes where first nobody ever saw lightning strikes. So it will have an influence, but what is the influence and what is the trend, we can't say right now. So we have to get much more information of cloud to ground data, out of cloud to ground data, but even for lightning location system data.
Okay, thank you very much. That means a lot of exciting research opportunities in the future.
Yeah,
the final question I can see, have you seen upward flashes?
Yeah, during my research period, I saw at least one upward flash. They're rather rare because they are normally appearing from high towers. I actually saw one appearing from a high transmission tower of a radio station, and it was really starting from cloud to ground. And I have analyzed the video, but I haven't used it that much, I have to say, because it's just one. I would like to gather more upward flash videos. But the guys from Brazil and even from USA, I think they got a lot of information about upward strokes, and also Aldis, because they have a direct current measurement on such a radio tower.
Thank you very much. Thank you very much for the answering of the questions as well. So for those of you, if you have further questions to Lukas, you can also type it into the chat box and he will be able to answer. Or after the presentation, you can send him an email, and I'm sure Lukas will be glad to share his experience and research with you as well.
That's true.
So can you stop sharing your screen so I can go back to my ones?
I stopped. I hope we're back.
Excellent.
Yeah, should be.
Let me share my screen again. So thank you again, Lukas, for your very interesting presentation and Q&A session. Now I would like to introduce our second speaker, Dr. Diptargha Chakravorty. Dip is a senior consultant with TNEI Services. He is an electrical engineer with over 8 years of experience in the power industry, including a 4-year PhD on the impact of demand response on system stability from Imperial College London. He specializes in modeling and analysis of transmission and distribution networks and automation of system studies. His core expertise includes stability analysis, grid integration of renewable energy, and power electronic converter control. He's currently the vice chair of the CIGRE UK NGN steering committee. The title of his presentation is Effect of Network Parameters on the Transient Overvoltage Phenomenon During System Restoration. So now, Dip, I would like to hand over to you. Could you please share your screen? Thank you.
Yep, thanks, Ying. I'll just share my screen. So, Ying, can you confirm that you can see my full screen?
Yes.
Okay, great. Yeah. So, yeah, thanks for the introduction. And I'll just straight on go to the presentation before I move on to the study. So let me just quickly introduce you to the innovation project on which all the results I'm going to present in today's presentation is based on, and the objectives of the project and the progress so far in the project. So this is a network innovation competition project here in the UK. It's called Distributed Restart. And the project partners are National Grid ESO, the Scottish Power Energy Networks, and TNEI. It's a specialist energy consultant here in the UK. Now, this Distributed Restart project, it's a 3 years project which started in January 2019. And it's a world first initiative to explore how DERs such as wind, hydro, solar, especially DERs which are connected at 33 kV or at 11 kV can be used to support system restoration. Now, the question could be that, why do we at all need to study this thing, or we are bothered about using DERs for restoration purposes? The reason being that traditionally, Black Start is a transmission-led approach where large conventional generations with self-start capability are used to restore the network after a blackout in a top-down fashion. And increasingly, going forward, these transmission connected fossil fuel generators are getting decommissioned and to meet the emissions target. So for this, we need to look elsewhere to procure services, Black Start services, which can help us for system restoration. And is one of the reasons why this project is the motivation behind this project, why we are exploring this using DRs for this purpose. And all the studies, the case studies, simulations, what has been done so far we share this annually, and we share it through the power and engineering trial reports. The last report which was published was this in July 2020. So all the case study networks, all the simulation results, you can find it here in detail. In this presentation, we are going to focus only on a small part of this Chaplain-Cross GSP test network. Just to give you a little bit of a background of the studies we have done so far in this project, 3 case study networks were considered, 2 in the Scottish Power Distribution license area, which is in Scotland, and 1 from the Scottish Power ManWeb license area in England and Wales. And out of these 3 networks, only 2 networks will be selected for live trial. And 1 live trial has already been conducted 2 weeks back. We have got back the measurements from the live trial. We've compared it with the simulation results, and it tallies quite well. Now, these 3 networks were selected based on a long list of other networks, and it was based on criteria such as having a good mix of different DR technology types, having typical topological representativeness of the license area. So these 3 networks were selected based on that. And in today's presentation, I'm just going to focus on this Chaplain-Cross GSP network, which has 7 primary substations, and it has got 4 DRs, out of which 1 DR here at Stevenscroft. This is a biomass synchronous generator, which will be used as the anchor generator. So by anchor generator, which we mean the generator which will impose the voltage and frequency. The red in this network is the in primary substation here. This is one of the 7 primary substations we have. One of the 7 primary substations we have in this network. And this is particularly important because in the results, what I'm going to present later on in the slides, we're going to use this substation in one of the case studies. And also I will highlight the Chaplain-Cross grid transformer. So 132 33 kV grid transformer. We have the Chaplain-Cross 33 kV bus bar here, we have the grid transformer, and then we have the Chapel Cross 132 kV bus bar. So the green box here, this shows the whole 33 kV GSP, and the 132 grid transformer, then the transmission line and the traction transformer, which is specifically the case study which we are going to present here in this presentation. So those are shown here in red. So everything shown in red are the ones which will be energized, and the rest of the network, it remains de-energized. Now, as you can see that we have got quite a few options to restore this part of the network. We can either go for simultaneous energization of the grid transformer, the unbalanced 132 kV overhead line, and the traction transformer altogether, or we can do them separately, or we can consider energizing a primary substation before energizing these bits. So there could be quite a few combinations, and that forms the basis of the different case studies we have studied here. Eight of them have presented here, and this kind of looks into the impact of different factors such as energization voltage, point and wave switching of the breaker system, loading condition, transformer saturation, and what these factors or how these factors influence the imbalance on the network or over voltage in the system. So I'm just going to quickly go through what these case studies mean. It's going to help us later on. We look at the results, but you don't have to remember the details. I'm going to again mention it later on in the slides. So case study 1 considers the grid transformer, the traction transformer, and the 132 kV unbalanced line. All of these are energized simultaneously at 1 per unit energization voltage when there is no primary substations energized beforehand. Whereas case study 3 is exactly similar to case study 1, only in this case, we consider that the primary substation has been energized prior to energizing the grid transformer and the unbalanced transmission line. In case study 2, we consider that the primary substation and the grid transformer, they are energized beforehand, and the system has already reached a steady state before energizing the transmission circuit. And case study 4 is exactly similar to case study 2, where we consider that no primary substation has been energized before energizing the transmission circuit. And case study 5 to 8 onwards, it's similar to case studies 1 to 4. It's only in this case, the energization voltage has been reduced to 0.7 per unit. So to look at the results, the first one would be trying to find out what's the impact of having a primary station energized before going for unbalanced transmission circuits. Now, before I go into the details and start explaining the figures here, I'm going to quickly mention about the two acronyms, TOV and SFO. So TOV stands for temporary over voltage, SFO is for slow front over voltage. And these two acronyms we're going to come across quite a few times in this presentation. These two phenomena occur for different reasons, but it can be triggered by the same event. I'm not going to go into the details of why it occurs, but I'm just going to assume that we're all familiar with what these phenomena are. Now, the figure shown here, the horizontal bar charts, I'm just going to take some time to explain it, how to interpret the results, so that it's quicker for us in the following slides when we have a similar graph. The y-axis of this figure gives us the point and wave switching instance of the circuit breakers, which are close to energize a certain bit of the network. The x-axis gives us a relative proportion of the over voltage at 3 bus bars. So the red bars give the over voltage proportion at 132 kV bar. The green one gives the voltage proportion at 33 kV bar. And the middle bit, the yellow one, gives us the over voltage at the terminal of the anchor generator. So if we look at a specific switching instance, suppose if we look at 6 milliseconds point and wave switching and compare it with 7 millisecond point and wave switching, we can see that the proportion of over voltage observed at 132 kV per bar is higher than what we see for 6 millisecond point and wave switching. So one key takeaway from these graphs is that the proportion of over voltage is not fixed at all the bus bars in the network. That is what it means is that a certain point on wave can improve the overvoltage or reduce the overvoltage at a bus bar, but another point on wave can actually make it worse. So it's not a linear function of the overvoltage is not a linear function of the point on wave across the network. So that's one thing. The other takeaway from this one is that if we compare these two figures, where we know that case study 1 and 3 are exactly the same, only in case study 3, one of the primary substation was energized before energizing the transmission circuit. So in this case, we can see that the green horizontal plots, the proportion of these green horizontal plots is much lower than what we see in case study 1, which means that if we have a primary substation or a demand connected in the network, that has a positive impact on the overvoltage at a bus bar. Later on when we look at further results, we will find out that the impact is not uniform and it has got the highest impact to the bus bar, which is closest to the demand connected. So now narrowing our view a little bit here, instead of looking at all the point on wave switching instant results, we're just going to focus on 2 point on wave switching instance. One is the maximum one. So the maximum ones are given by the light blue bars here, and the minimum one. So what it shows is that the point on wave switching instant, which gives us the worst case and the best case over voltage at 3 bus bars here. Once again, to interpret this graph, on the y-axis, we have got the per unit temporary over voltage observed at these bus bars. And these are calculated in per unit in terms of the phase, 1 per unit phase voltage. So if you have to calculate the absolute value of the voltage, this is how we have to calculate it based on the per unit value, what we observe here. Now, the key takeaways from this one is if we compare these two case studies, once again, we see what we observed in the last slide, that having a load impact has got a positive impact on the over voltages observed at the different bus bars. And we can see here from the peak values observed and also the minimum TOV values observed at different bus bars that both the minimum and the maximum TOV reduces all the bus bars. However, if we calculate the proportion of reduction of the maximum TOV values connected has the maximum decrease in TOV. Now we're going to look at the same case study, but at the time domain results, and we cannot look at all the switching instance. So the results presented here correspond to the worst case point and wave switching results for chapel cross 132 kV and chapel cross 33 kV. What we see is that in case study 1, when we don't have any primary substation energized, we observe a temporary over voltage at both the bus bars, whereas with the demands connected, the temporary over voltage disappears in both the bus bars. And in case of 132 kV bus bar, the switching transient can be seen here, whereas at 33 kV bus bar, the switching transient disappears as well, and we don't have any appreciable transient at all in this bus bar. Now looking at the impact of saturation on the over voltage at a particular bus bar. So by saturation, what we mean here is that the grid transformer is already energized and the system has reached a steady state before further energizing or closing a breaker, like in this case, the 132 kV unbalanced line. So what we see here again is that we already know how to interpret these graphs. So the key takeaways would be that when the grid transformer energization is done prior to energizing the transmission line, then the influence on the 132 kV and 33 kV over voltage is not that significant. Like we have got minimal influence on 132 kV, whereas on 33 kV, we see that there are slight increase in the over voltage, but the proportions as such doesn't change by much. And what we also see is that the nonlinear effect of point-on-wave on the proportion of overvoltage, what we see here and also on the previous slide, that seems to be quite uniform when we do not have saturation, impact of saturation considered. Looking again from the point of view of the worst and the best case scenario, we see that in case of Chapel Cross 132 kV, we can see the maximum and the minimum overvoltages have reduced when we do not have any transformer saturation considered. But in case of 33 kV Chapel Cross voltage, the overvoltage seems to have increased in this case. This is also something we can see from the instantaneous response. When we do not have the saturation considered, the temporary overvoltage observed here appears much quicker, whereas when we have no saturation considered, that gets delayed by quite a lot. And in case of 132 kV, the peak voltage observed in this case is slightly lower than what is observed in case 1. But in case of 33 kV, it increases marginally. So what tells us is that we do not have a clear answer to if energizing a transmission line with the grid transformer will always lead to a favorable result at all the bus bars. It can potentially help in case of overvoltage in some of the bus bars, but it might make it a bit worse in another part of the network. Now, looking at the impact of energization voltage. So by energization voltage, we mean when we close the breaker, what is the voltage imposed by the anchor generator. In this case, we have reduced that voltage to 0.7 per unit. And if we compare the maximum and minimum TOVs observed at the 3 bus bars, we see that there is a definite improvement, and reducing the energization voltage helps in reducing the peak TOVs observed in the network. And similar to the previous case, if we compare the percentage reduction in the maximum TOV and the minimum TOV, we see that it's quite uniform across the network. So we can say that the energization voltage has a positive impact on the voltage and the voltage transients observed in the network, as well as this impact is quite uniform across the network. And then we're going to look at the impact on the voltage unbalance. In this case, the x-axis would give you the point-and-wave switching, and the y-axis gives you the voltage unbalance in per unit. And this is measured at the terminal of the anchor generator. Now, the difference between case study 3 and case study 7 would be that in case study 7, the energization voltage has been reduced to 0.7 per unit. The maximum unbalance observed is 8% in this case when we have a 1 per unit energization voltage, and 5% when we have a 0.7 per unit energization voltage. So the key takeaways from here would be that voltage unbalance is a function of point-and-wave switching and energization voltage, both of them. And the peak unbalance we can reduce the peak unbalance if we adopt any of these intervention techniques. And in both cases, the peak unbalance is slightly more than the P29 limit. So one option would be that we can tweak the negative phase sequence protection of the generator to adapt it during the duration of the restoration, so that due to this unbalance, the generator doesn't trip. But the 5 to 8% unbalance observed here is not a problem from generator's machine design perspective. So the synchronous machine can withstand this unbalance, but it's the protection setting which will cause it to trip. So we can update that one. Or the other option would be that we don't restore any unbalanced transmission network or any other unbalanced bits of the network until the network has been sufficiently restored and it's strong enough to restore any unbalanced bits of the network. So to summarize the key findings, that temporary overvoltage or slow front overvoltage In all cases, we have studied specifically for this unbalanced 132 kV line energization. They are within the IEC 6071 limits. So it's not a problem as such from live trial point of view. The damping provided by the load helps to reduce both the maximum and minimum peak TOV. And the amount by which the TOV reduces is found to be not uniform across the network, and the maximum impact will be at the bus bar, which is closest to the demand. The interaction between a circuit and a transformer energization is a complex phenomena, and it cannot be said with certainty that the energization of the transformer separately will always have a positive impact, or will have a positive impact equally or at all the bus bars. But for the energization voltage, we found that it has got a uniform impact across all the bus bars, and it helps to reduce the peak TOV and SFO. So this can surely be used as a method for reducing voltage stresses on the network. And for the live trial a couple of weeks back, we actually had to adopt this method to reduce the over voltages and avoid from tripping the generator on over voltage. And for voltage unbalance, we found that point and wave switching and energization voltage both has a positive impact, and it can help to reduce the unbalance in the network, especially if we are energizing network components like this 132 kV unbalanced line. And from all these case studies, and not only for these specific studies which we have, which I've presented here, but if you look at our July 20 PET report, you will find from all the case studies, point and wave switching has the highest impact on be it voltage transients or unbalance. So if a particular case study shows that there is a particular problem with voltage transients, and it is possible to energize the network as such, then probably point and wave switching could be a good option in that case to make it happen, or for that particular restoration sequence, we might have to use such a method, such an intervention technique. So with that, thanks a lot for listening to my presentation. You can reach me at, I have my email ID is supplied here. If you have any questions now, I'll be happy to take.
Thank you very much, Dip, for the very interesting presentation on a major project here in the UK. Is there any questions from the virtual floor? I can't see anyone. Personally, I have a question. What do you see the impact, for example, if more power converter interfaced generation getting into the power system? How does that affect some of your conclusions? For example, the power point and wave switching impact and energization voltage on the unbalance.
Yes. So one point here is that in this project, our starting assumption was that any GSP which is being energized, or any island which we form, it's always using a synchronous machine. So that will impose the voltage and frequency. And then later on, we're going to connect the inverter interfaced generations. So long as we are not energizing the network, like imposing the voltage and frequency using these in the inverter interfaced devices, so the energization of the network or energization of a transformer, these wind farms or solar farms, they don't have to do it as such. They're not doing it. So if they have to do that energization, then what the impact of having point and wave switching, or are they able to do it without any such intervention techniques? That is something something still we have to explore, and which has not been looked into in this project. But what this project has looked at is that all these restorations would be done by the synchronous machine first, and then the wind farms and the solar PVs will connect to the network. So in that way, there's no problem as such to have inverter-based technologies in there.
Yeah, okay. Thank you very much. I can see another one coming in the chat. Regarding the point and wave modeling with the transformer, have you considered switching different phases at different points and wave, and only 3.3 millisecond delay between the phases?
No, so this is also something like, I know that when we have the different poles of the breaker, when they close, they don't close at the same time, and there could be differences in that, which happens in reality when we close the breakers. But for the simulation purpose, we haven't looked at closing it at different times. We just looked at assuming that all the breakers are closing at the same time, and what's the worst case situation in that case.
Okay, thank you very much. If there are no more questions, thank you very much. Dip, again, if you have further questions or interested in the project that Dip mentioned, the innovation project, feel free to email him, and I'm sure he's happy to share his research and outcomes with you as well.
Yep, sure.
So with that, we are coming to the end of our session. And finally, I would like to share you 2 links. So if you're interested in joining both CIGRE Austria NGN and the CIGRE UK NGN, please visit our website and also follow us on our social media. And as the current pandemic continues, we will be holding more interesting technical webinars in collaboration with other NGNs around the world in the future. So if you're interested in such an event, please let us know and join the NGN and follow us on the social media. And I'm happy to see you in the coming webinars in the future. So and finally, thank you again, Dip and Lukas and Manuel, for taking the time to prepare and present today. And thank you very much.
Thank you.
Thank you
Thanks,
for the
everyone.
opportunity. Thank you.
Okay, thank you very much, everybody, and have a nice day.
You too. Bye-bye.
Thanks.
Bye.
Bye.
Bye-bye. Thank you.